Okay, on to example 2. So we've got the sine of x is equal to the cosine of 2x. And we're going to look for the general solution equations and then the particular solutions between 0 and 2 pi. And then we're going to make sure that we mark them as ordered pairs on the graph. That's given. All right, so in order to solve, we've got the sine of x is equal to the cosine of 2x. Now I want to make a note here. The angles are different. On the left side, we have just x. On the right side, this gets more complicated. We've got 2 times x. And the problem is we can't do anything when the angles are not the same. We can't use properties to combine when the angles aren't the same. So the first thing we're going to do is we're going to work with that left side, or excuse me, the right side, and we are going to expand the cosine of 2x in order to make this problem a little bit more accessible. Now, there are many different ways that we can expand the cosine of 2 times an angle. There are 3 ways that we could go. And there is more than one way of solving this. For this example, I am going to use, what am I going to use? Cosine squared minus sine squared. We could do that. How about 1 minus 2 sine squared? Right? And that way, that gets everything in this problem in terms of sine and only sine. Okay, then what I'm going to do is I'm going to move everything from the right-hand side over to the left so that I get the right-hand side equal to 0. What that's going to look like, I'm going to add 2 sine squareds of x to the left-hand side, and then we're left with plus sine x, and then minus 1, that is all equal to 0. So now I have 0 on the right-hand side. We can start thinking about how to apply that zero product theorem. So this might look like a polynomial that we have factored since algebra 1. Let's say instead of sine x, I represent it as like a different variable, like y. This could become 2y squared plus y minus 1. That is something that we've been factoring since algebra 1. We're going to do the same thing. We're just going to have words instead of variables. So I can factor 2 sine squared of x plus sine of x minus 1 into this. Let's see here. We're going to have plus 1 and minus 1 like this. So 2 sine x minus 1 times sine x plus 1. And the zero product theorem then tells us that either one or both of these factors must equal 0 if their product is 0. Okay, so going forward, right, we have the sine of x is equal to 1/2, or the sine of x is equal to -1. Now, those are going to yield 2 principal values. The first principal value is going to come from the angle whose sine is 1/2. The angle whose sine is 1/2 is going to be pi over 6. And then the angle whose sine is -1, that is negative pi over 2. Remember, we're sticking with the range of inverse sine, which is negative pi over 2 to pi over 2. So at negative pi over 2, our sine value is -1. Okay, so then we move on. We are looking for the general solution equations first. Now, these both yield principal values from sine. So we're going to use the general solution equations for sine in all 4 of the equations we represent. Okay, so first with that principal value of pi over 6, remember that the first sine equation is the principal value plus 2 pi n. The second is going to be pi minus the principal value plus 2 pi n. So pi minus pi over 6 is going to give us 5 pi over 6 plus 2 pi n. And then we go on to this second principal value. That's the third general solution equation. That is going to be our principal value plus 2 pi n. And then the fourth one is going to be pi minus that principal value plus 2 pi n. So pi minus negative pi over 2, that actually becomes 3 pi over 2 and then plus 2 pi n. So those are our general solution equations for this problem. Okay, and remember that at the very beginning, we just had to make sure we use the right property. And then lastly, we're going to look at those particular solutions. So again, if I'm going to make a table that keeps track of all of these equations and we plug in values for n and see what happens, those are where those solutions are going to come from. I'm going to do it without the table today. So I'm just going to list the solutions in order from smallest to biggest. So let's see. We would get pi over 6, we get 5 pi over 6, and we get 3 pi over 2. Those are the solutions between 0 and 2 pi. Now, remember that we're going to mark these on the graph. So we're looking for where these two curves intersect. So I see this first point here. I'll call it point A. Down here, B, and then moving forward all the way down here, this is that third intersection point. I'll call that C. Okay, so what we want to do is we want to find the ordered pairs that represent each of those points. So pi over 6 is the smallest value. That is going to be the x value of point A. And then moving on, 5 pi over 6 is the next smallest value. That'll be the x value, the x coordinate of that ordered pair B. And then lastly, 3 pi over 2, that is going to be our last point at point C. So those are the x values of each of those points. Remember what we're going to do. We're going to take those values of x, and we are going to plug them back into one side of the equation in order to get y. Now, in this case, what side do we want? Doesn't really matter. I think evaluating the sine of that angle x is going to be easier than the cosine of 2 times that angle. We'd have to multiply the angle by 2 and then take the cosine. So I'm going to plug it into the sine of x here. Okay, so the y value, or the y coordinate of point A, is the sine of pi over 6. The sine of pi over 6 is 1/2. All right, next, the value for B, again, the sine of 5 pi over 6 is also 1/2. And when we look at the graph, the y values are exactly the same, right? So that kind of matches up with what we're seeing graphically here. And then the last one, we've got the sine of 3 pi over 2. Well, the sine of 3 pi over 2 is just -1. So that means that we must be scaling here by by 0.5, right? Okay, and then along the x-axis, we're going 0 to 2 pi again. Okay, so those are the particular solutions for number 2, marked on the graph with the ordered pair coordinates.